Okay, recap. We talk about curvature now, right? The main purpose is to understand how matter acts to curve space-time. For that, we need to first understand what does it mean that the space-time is curved. That's why we do curvature. Then we're going to finish curvature, and if everything goes well, we'll also maybe have time to derive Einstein's equation. So what did we do? Quick recap. So we did a parallel transport. Right. We said a parallel transport is when I take a vector and I just move it along a path, right? Which path is something which is always defined on any manifold, parallel to itself. Parallel to itself in the sense that the covariant derivative along the path is 0. By the way, I forgot to ask you, how was the tutorial on Monday? I assume people were there.
It was okay.
Okay. Not okay.
Too much time for too little time for too much.
Too little time for too much material.
It took an hour and a half instead of a.
That's strange. I know what we were supposed to teach you. It's not supposed to take that long, unless you ask many questions. But I mean, it's good. But then again, you know, we're not kids. If you're here by definition, you're not kids, which means that you're supposed to be going to elaborate, learning things yourself.
The recording stopped early.
Recording
all sorts of technical issues. It's fine.
Okay. Again, I asked to record, but I'm not in charge of technicalities here. My understanding is that starting next week, some of you have on Monday something.
Yes.
Okay, I may go on Sunday again, and I made another table to see, because I see that now, I don't know, people that are now maybe less than people that were there like a few weeks ago. So we'll see if there is another time which may suit people around here. Okay, so we spoke about parallel transporting of a vector. Which was essentially d b over d lambda mu. By the way, in many textbooks you'll find it as written in a slightly different way than I'm writing it here. It's a dv over small v. That's also something which you find in textbooks if you go to the literature, which is really dx sigma over d lambda plus sigma v mu equal to 0. That's the equation of parallel transport. And then we spoke about curvature and we defined the Riemann tensor. Which is a 1-3 tensor. R rho sigma mu nu v mu gamma rho nu sigma minus d nu gamma rho nu sigma plus gamma rho nu lambda gamma lambda nu sigma minus gamma rho nu lambda gamma lambda nu sigma. There is a great conspiracy here, as I'm sure you've noticed, because gamma, as we say, is not a tensor. So none of the terms in the right-hand side is a tensor, but when you combine them together like that, it is a tensor. It's a 1-3 tensor, which tells us about the curvature of space. I said, giving you only half proof that the necessary and sufficient condition for the metric to be equivalent to Minkowski metric is that the components of the curvature tensor vanish everywhere, and that the metric has 3 positive and 1 negative eigenvalue. I'm going to write it down, and you got the idea. And then we spoke about algebraic properties of the Riemann tensor. basically we specify 4, right? That it's symmetric under interchange of the first pair of indices with the second pair. R rho sigma mu nu is R mu nu rho sigma. So it's anti-symmetric in exchange of the first 2 indices. R rho sigma mu nu is minus R sigma rho mu nu. So minus R rho sigma mu nu to R sigma rho mu nu. And it's cyclic. Again, of the only last 3 indices, R rho sigma mu nu plus R rho mu nu sigma plus R rho mu sigma mu is equal to 0. This is anti-symmetric with respect of any single index.
Yeah, so after the rho in 1, it's sigma, right?
What? After the
rho in the first equation, it's
rho sigma. Then of course it's anti-symmetric in the last 2 indexes. We made a contraction to define the Ricci tensor. R mu nu is R lambda mu lambda nu. And the Ricci scalar simply R mu mu, which is G mu nu R mu mu. I think that's as far as we managed to go last time. Any questions? Questions? So, everything is clear? If I ask you that on the exam, you know what to do.
Doesn't the fourth identity follow from the second identity?
Sorry?
Doesn't the fourth identity follow the second identity?
In fact, yes. You can simply see it right away. Most of it you can see just right from looking at the definition. So basically the answer is yes. Didn't really have to. Just derive it.
You did quite a bit of, when you so many times assume that the metric is symmetric. Do we make this assumption always? In the symmetry
In this course, yes.
Because
in higher, again, this is introduction to general relativity.
Because in the symmetry of the gamma Christopher symbols, to prove that they are symmetric and the exchange in the bottom of this, we have to assume that the metric itself is symmetric.
No, we did not. It follows from the definition of the affine connection. We just do a second derivative. Right?
I'm not sure. I'm not 100%
I am sure. We took the definition was when we got the affine connection, right? I remind you that, right? Gamma lambda mu. Gamma lambda mu nu was b x lambda over d psi alpha, d squared psi alpha over d x mu d x. So it's just symmetric if you're assuming that the
okay, this is symmetric.
Just because of the symmetry of partial derivative.
But to get this form of the derivative, so I think we have some way in the long derivation we have to assume
it was not hidden at the time of.
Let's assume that this is correct if it is symmetric.
No, I did not assume it. I just defined it. I did not have any assumption. It just follows from the definition. Just follow the definition. You can go over all your notebook. Just follow from the definition. There was no hidden assumptions here. Now, it's true that in this course we're not going to use metrics which are not symmetric. Now you can think of metrics which are not symmetric. but not in the realm that what we're doing here.
In the symmetry properties of this symmetry of G.
I don't think so. No. This we just use G to lower the first.
Yes, but we expanded this in terms of derivatives of G and derivatives of everything else.
No,
We have
you have here the gammas, the definition is right here.
Yes, I know.
You have here the gammas, you have here the derivative, that's all.
To expand the third identity, we have to expand the R in terms of G.
Right.
To cancel some terms out, we have to.
I don't think so. Anyway, it's not relevant to what we're going to discuss. If you want to ask more about this symmetry and anti-symmetry, then maybe we can do this discussion at the end of this lecture. Yeah.
Can we really use the symmetry of G in the course, like in the test at home, even if it's not given?
If you know what is G, then yes. You can use all the properties, right? Then. Okay. Why did I care about that? Because I want to look at the Riemann tensor in n dimensions. Leave that now for now. So general description of a Riemann tensor in n dimensions. What?
The same description.
The same what?
Description.
Wait. The thing that I care about, so Riemann tensor has 4 indices. Right, so how many different components does it have? What?
256.
156. That's quite a large number. But because of all these symmetries, many of them are not independent. So the question that I'm interested in answering right now is how many independent different components does the Riemann tensor has in n dimensions, right? So how many independent components does the Riemann tensor have? Okay, so the first is to note, right, we have the following. It's anti-symmetric in exchange of the first 2 indexes, anti-symmetric in exchange of the last 2 indexes, and symmetric is exchange of the 2 pairs of indexes. So how many components would that have? Independent. So if I have a symmetry, I can think of it, right, as R. Wait, let's start with the symmetric. Mu nu rho sigma. So I can think of it as a matrix which when I 2 by 2, which when I exchange, it's symmetric. So how many components would it have? Independent?
n plus 1.
Right. M plus 1 over 2, right? So it will be M plus 1 over 2. Now I'm looking at this M, right? M contains 2 terms, which is anti-symmetric. So how many independent components will it have?
Same minus 1.
Same is a minus 1, right? So really, what this will give me is an n minus 1 over 2, 1/2, and then n minus 1 over 2 plus 1, right? So this is called from the symmetries. This is this, this. So if I expand that, I'm going to save you the algebra. It's 1/8 n to the 4 minus 2n cubed plus 3n squared minus 2n. Okay? That's from the symmetries. Again, this is the number of independent components that the Riemann has.
We didn't use the third part.
What?
We didn't use the third part.
Yeah, I did not use it yet. I need to use it. So what does the cyclicity mean? If I look at the totally anti-symmetric part, R is 0. What?
So you do the choose.
True.
What?
Choose. Choose one and choose the other.
Right. So how many total do I have? So this means that the total anti-symmetric part vanishes. I don't know, we didn't really touch upon that because it's not really crucial, but the way to write it is R rho sigma mu nu. This is the total antisymmetric part of R is equal to 0. So how many further constraints do we have? N minus 1. So we have
N minus 3 divided by
so minus n minus 1, n minus 2, n minus 3 divided by 4 factorial.
Yeah.
Why is that?
What? Because I can choose for the first term, I can choose whatever I want. For the second term, I can choose n minus 1. For the third term, n minus 2. For the last one, n minus 3. Think of it a little bit. It's combinatorics.
We don't have
What?
forcing on just the last instance. Or just
No, for the first index, I can choose
Can choose
whatever value I want.
yeah.
For the second, I can only choose n minus 1. I cannot choose the first one.
Why can't we
This will be 0. Because it's not an anti-symmetric part. Again, think of it for it.
Oh, because of the anti-symmetry of the exchange of the first two.
Yeah. So I have that minus that. That's 24. Again, I'm going to save you the algebra. The end result is 1 over 12 n squared times n squared minus 1. This is the number of independent component of the Riemann. Independent components of Riemann tensor. So, how many independent components does the Riemann tensor have in one dimension? 0. About 4 dimensions? 20. It's quite neat. Okay. Now, there is another identity. These are all algebraic identities, but there is another identity, which is a differential identity. We're going to go back to it. How many does it have in 2 dimensions? 1. That's the Gauss curvature.
Oh.
Okay, so there is another identity, identity, but it's a differential identity. And the name is the Bianchi identity. Again, there are many Italians in this business. So I'm going to look at the covariant derivative of the Riemann tensor evaluated in a coordinate system in which the fine connection vanishes. So covariant derivative of Riemann evaluated in coordinate system in which gamma is equal to 0. You can always find a coordinate system like that. Why not?
For all them?
You can't always choose a coordinate
For
system.
specific
Tensor
values or
zero
for
out.
all?
Specific coordinate system where this gamma vanishes, not its derivative. That I can,
At a certain point.
yes,
And why is that?
because it's going to be easier for me to derive the
No,
equation.
why can't you choose?
So I always have such a coordinate system, right?
Just
What do you mean why? I said that. I mean that's. We said in every point in arbitrary potential field, I can always select locally inertial coordinate system, right? It's very basic. So, what do we have? Now it doesn't mean that the first derivative of gamma vanishes, right? But gamma itself can vanish. So, have the lambda of r rho sigma mu nu is now it just be a regular derivative. And so partial derivative with respect to lambda of r rho sigma mu nu. It's 1/2 in lambda. Then I don't need the gamma terms because they vanish, but I do need their derivatives. D mu d sigma g rho nu minus d mu d rho g nu sigma minus d nu d sigma g rho mu plus d nu d rho g mu sigma. Can do that. It's totally legal. Right? All the gamma terms vanish. Now, what do I do with that? What do I do with that? Of course, I take a cyclic sum. So,
You use the identity.
what?
You use the identity of the sum of three R's are 0.
No, this is no. There are no zeros here, right?
Oh,
Then,
you
I use
the
that
identity.
to. Yeah. All the g's are all the gammas were 0. Then I just remove it. Right. So lambda r rho sigma mu nu plus lambda rho r sigma lambda mu nu plus lambda sigma r lambda rho mu nu is equal to, yeah, of course, right. But just copy that, right? So you have that 1/2 d lambda d mu d sigma g rho mu minus d lambda d mu d rho g mu sigma minus d lambda d mu d sigma g rho mu plus d lambda d mu d rho g mu sigma. That's the first one, and then the second one, just exchange of indices, d rho d mu d lambda g sigma nu minus d rho d mu d sigma g nu lambda minus d mu d nu d lambda g sigma mu plus d rho d nu d sigma g mu lambda plus d sigma d mu d rho g lambda nu minus d sigma d mu d lambda g nu rho minus d sigma d nu d rho g lambda mu plus d sigma d nu d lambda G mu rho. Now is the fun part. Everything cancels. Right.
Why does this zero out?
What?
Why does this zero out?
Oh, that's what. Why is it what?
Why does this top term zero out?
Why is it?
Why does it zero out?
Why? I cannot understand.
Why does it vanish?
Well, I just explain. I shouldn't write it. This cancels with this. Right.
Wait, what about the lambda of the R's?
What? What do you mean? Just written here.
Ah, yeah.
Everything is fine. This cancels with that. This one cancels with this one. Right. Gee, this one cancels with this one. This one cancels with this one. And this one cancels with this one, so we end up writing 0 here. As anticipated properly. Now we derive this equation in specific coordinate frame, right? But what type of equation is that? It's a tensorial equation. Tensorial equation, if it's true in one frame, it's true in every frame. So it's always true. Okay? This is called the Bianchi identity. And in short notation, this is written as lambda r rho sigma mu. It's anti-symmetric here. Now we're getting quite close to finishing the big mathematical part. Just before, we need to do just a few more lines. So if we take this Bianchi identity and contract it twice, so I have a 0 equal, I'm going to contract it with a G mu sigma G mu lambda of what is written here. Lambda r rho sigma mu plus lambda rho r sigma lambda mu plus lambda sigma r lambda rho mu. I'm just doing the contraction. Let's see. So here I have a nabla mu. This is a nu and sigma, but I can exchange them twice. It's not changing anything, and then I have the contraction because it would be a nu, right? So I end up with an r rho mu. Here I have, again, I'm using these exchanges twice. So I have a mu lambda, this rises, right, this goes to mu. With that, I exchange it, I get a minus sign, I contract, I get an r sigma mu. I'll multiply it again with r, with g mu sigma. What do I get? Minus I had, nabla rho, and r. You with me? Because I'm just following a few steps here at a time.
Not exactly. What did you do?
What did I do? I have. Let's look at that point here, right? I'll use a different pattern. G mu lambda r sigma lambda mu nu. I write it as r sigma mu, right?
So this is a side derivative.
What?
This is a side derivative.
No, it's okay. Ah, that by the way answers your question, right? What is the covariant derivative of g? 0. So I can always insert it inside.
Oh.
Ah, That is why I'm also allowed to put the derivative up. Because if I have r, I don't know, a mu, it's just g mu a.
So this is how it's defined.
Yeah. It doesn't mean anything physically, but practically I can always do it. But that answers your question for last time. Right? Because you see what I am always allowed to put g inside the covariant derivative because the covariant derivative of g is 0. That's the metric compatibility. Okay? So I put the covariant derivative g mu. Oh, I have a nabla rho r mu sigma mu sigma. So I exchange the indexes. I get a minus here, right? So this is a minus nabla rho r mu sigma mu. This is a contraction. So what do I get? The reaching. So this is minus nabla rho r sigma mu. Nabla rho r sigma mu. I still have the g nu sigma. So I use the g nu sigma here. G nu sigma. So I get the minus nabla rho r nu. Which is? Which is Ricci scalar. So that's what's written here. And here again I have g nu sigma nabla. This is plus nabla mu. And g mu lambda, again I contract it. Mu and mu is contraction, so I get an r rho. Now, mu here is a dummy index, mu here is a dummy index. And this is equal to 0. So I can exchange mu with mu. It's dummy index anyway. So I end up with nabla mu r rho mu is equal to 1/2 nabla rho. It's okay. You see what I did here? You simply need to get yourself a little bit more familiar. Get some experience just using this. It's really just contractions. Okay. The only thing that you can think of is that I put g inside the covariant derivative because covariant derivative of g is 0. Yeah. So that leads us to define a new tensor, which is called the Einstein tensor. We're quite close now. So we define the Einstein tensor. G mu nu is r mu nu minus 1/2 r g mu nu. That's the definition. The Einstein tensor. And this Bianchi identity with twice contraction is written as what?
The mu, g, mu.
Yeah, exactly. This is simply written as nabla mu g mu is equal to 0. So you're going to see shortly, possibly even today, this is not just a mathematical game, this has a important physical meaning. So far, we just play with the math. Okay, just need to follow all the rules and see that I was not cheating on you. Yeah.
The reason that's true is because you take from the equation on the left, you move the right one to the left, and then you multiply and you multiply by g and its inverse, so the index goes up. The rho goes up, right?
Yes. Replace rho with a nu. Again, I'm very free. if you don't have enough experience, it can be very tricky. But I'm very freely changing names of dummy indices, and when I see the same index that appears twice, I know that I can change these switches with any other letter that I want. Yeah? Okay, before we move on, now it's time to make a stop and have a few examples. Any questions or technicalities?
Just to make sure, the Bianchi identity is this equation?
This is the Bianchi identity. This is the Bianchi identity. This equal to 0.
Oh.
This is the Bianchi identity. And this is the twice contracted Bianchi identity. Twice contracted. Here's that. Or that. Cool. Any further questions? Okay. Clear? So let's do a few examples. How many? Oh, it's written here. Anyways. So we said, how many independent components does the Riemann tensor has in one dimension? 0. What does it mean?
Because you have only one type of
Can a one-dimensional space be curved? No. I mean, this is not curved? It's not curved. If I have an ant, again, I'm inside the space. I'm an ant, right? Inside the space, you don't look at how this space looks like and how it is embedded in higher dimensional space. Inside the space, this line is not curved.
Just pull at the ends.
You can pull if you want to, right? But this, you can only think of it like that because you're thinking of that line or rope embedded in a higher dimensional space.
Pulling at the ends.
But if it's not embedded in anything, it's just if the world is only one dimension, single dimensional, there is no notion of curvature in one dimension.
This is one dimension exact
one.
time, or this is total one dimension?
It's one dimension.
Space time.
Space time. It doesn't matter. Space time, it doesn't matter. Space time that's a physical interpretation.
So space
The
time.
calculation that we did for the Riemann tensor is completely general. Right? I specify a metric, I can specify a metric for whatever I want. Right? Physically, I would specify a metric for a 4-dimensional space-time because that's the world we live in. But nothing prevents me from specifying a metric for a 2-dimensional space, Euclidean space. Right? I can do that. Actually, you're supposed to do that as part of your homework. Right? You can specify whatever metric you want. We did it in some examples previously. But that's fine. What about 2 dimensions?
There is only one.
There's only one. So 2 dimensions, so that's 1 dimension. 2D, there is 1. Independent component. Which means that, in fact, everything we need to know, all the information that there is about the curvature of a 2-dimensional space is given by one parameter, which will be the Ricci scalar. Right? By the way, 3 dimensions, how many?
6.
How many?
It's 3 dimensions?
Yeah, 3 dimensions.
6.
6. It's getting more and more complicated when you go to higher and higher dimensions. Right. What about the cylinder? What's the curvature of a cylinder?
0.
0. You all see that? It's not curved at all. You can just cut it here and open it. So really, it's a space where I identify one side with the other side. get a cylinder by taking my notes and put it like that. It's a cylinder. If it was flat initially, it's still flat. Again, I'm looking only from the point of view of somebody on that space. What about the torus?
It is correct.
What?
It's just
Zero.
Oh no, it's
still
not
taking
that.
your
Actually, that's a bit tricky point here. It's called conformally flat, which means that you can find a metric which will be flat. Because the torus, again, you get it by taking a piece of paper and identify the two edges on one side and two edges on the other side.
You need also to say how you connect them.
But I could, in principle, do it like that,
Get a twist.
and then twist it like that if I could. And it could be
But
a
you
twist.
can also. Does it matter?
Yeah,
if
it's quite a tricky thing. This is exactly one of those things that mathematicians really love. That's why it's conformally flat. You'll see that in one of your homework. You have to actually do it. You see that you can get a metric which is looks flat.
אתה צריך כאילו גם להגדיר איך אתה מחלק. אתה צריך להסביר איך אתה מחלק.
No, I identify.
No, it's
I
a
identify. If I go along this direction, when I reach the boundary, I just continue from here.
אבל אתה יכול גם לחבר אותו הפוך, להוסיף טוויסט.
I can do many things. I can do many things, right? But the idea is clear. I identify. I take to get the torus. I'm not telling you how I get all the possible metrics, right? I'm not talking about Mobius stripping. To get a torus, I take a piece of paper and I simply identify one edge with the other edge.
Don't you need to connect them to write an error or something so it's be clear how you connect?
Yeah, the idea is just to show you curvature in 2D.
So
Ken,
question. I heard a long time ago about some theorem that for a two-dimensional space, the Gauss curvature can be calculated by multiplying the line with minimal curvature through a point and the line with the maximum curvature.
yeah, there is something.
Because in a torus and in a cylinder, there's a line which is just straight with zero curvature.
Yeah.
Is there some more general theorem that allows us to calculate the curvature of the point by some special geodesics that go through that? Like a generalization?
Generalization, I'm not aware of, but I'm not a mathematician, so there could be that. What about the sphere?
Sure.
There we go. What about flat? How do we know it's flat? You cannot map it to anything in space. You cannot do a map. But we know how to do it now. So we have a sphere, we can choose a metric. What will be the metric? So the squared. I'm talking only about the surface of the sphere, right?
Yeah,
So let's say it's a squared. I call it a
A
squared.
Theta squared.
We'll have d theta squared plus sine squared theta d phi squared. This is A is the radius. Phi. So I think you were supposed to look at the metric for that at home. So let's go over it quickly. So the only non-zero connection coefficients, gamma, theta, phi is minus sine theta, cosine theta, and gamma phi, theta phi is gamma phi theta is cotangens theta. And then the only well, we just need one component of the Riemann tensor, really. So R theta phi is d theta gamma theta phi minus d phi gamma theta phi plus gamma theta the lambda, it's a rotation, gamma lambda phi minus gamma theta phi lambda gamma theta phi right? Why only one component?
That's one independent.
Because all the other components I can get by the symmetries of the Riemann. Right? If I want to know R phi theta, be equal, right? Just switch indices. So what do I get? D theta, gamma, theta, phi, phi. Come on, let's write it down. Cosine, sine squared theta minus cosine squared theta. This one, gamma phi of the d phi of gamma theta phi theta phi.
Nothing else.
Nothing, that's a 0, right? Yeah, plus minus 0, plus this also gives me a 0. That's a minus, this is minus sine theta, sine theta times tangent theta. So I end up with a sine squared theta. Just a second, if you want to lower the indices, we have an R, theta phi, is just a G, theta lambda, R lambda, phi, theta phi, G theta theta, R theta phi. What is G theta theta? A squared. This is A squared sine squared theta. Questions?
The question is that previously it said that the curvature of the torus is 0, but it's not 0 because if you try to connect this at the curvature.
So the torus is something which is a little bit more tricky. It's a conformal flat. It's not flat.
So the curvature is not 0.
It is 0. It means that you can always find a metric which is up to a constant equal to a flat.
And the curvature doesn't change with the metric.
I have to think of it. Not that I understand right now. Let's finish with this example. What about the Ricci? So the Ricci tensor, or you knew is G alpha beta R alpha beta alpha sorry mu beta nu, and you have that R theta theta is G phi phi R phi theta phi theta. Is R phi theta phi theta? Is R phi theta phi theta?
Same.
It's the same, right? Just change once, change two. Right? So it's the same. It's R theta phi theta phi. Yeah? What is G phi phi?
A squared sine theta squared.
1 over. So what do I get? R theta theta? 1. R theta phi is R phi theta is 0. R phi phi is G theta theta. R theta phi. What is that? Yeah, that's a sine squared. And the Ricci scalar. So what? Yeah? It's constant, right? That may be somewhat associated, related to the question of symmetry that I was asked earlier. Right? It's independent on the location. of the space, right? That's another way of saying that this is a maximally symmetric space. Okay. Well, you could think of a space which was like American football ball, ellipsoid. To have a curvature, positive curvature, but it's not going to be constant everywhere. So you know, it means what you think it means. Right? Constant everywhere. Meaning it's a maximally symmetric space. Okay, another thing is that it's not just a constant everywhere, it's also what? It's positive, right? So we said that this is positively curved. Right? So this is always positive, or greater than 0 means it's positively curved. So we said that a sphere is a maximally symmetric space with positive curvature. And the larger A is, then it gets to what? It gets closer and closer to flatness.
What would be an example of a space with constant negative curvature?
That would be my question to you. Yeah, it's hyperbolic, right? So that is something which is much more difficult to imagine. If you use your imagination, it's like a saddle. Because in one direction, I mean, if you're standing somewhere on this sphere, right, the sphere curves in the same direction everywhere you look at, right? It always curves in the same way from you. So a negatively curved space would mean that it curves in opposite directions depending on the way you look. So if you look something like a saddle. If you're standing here, it will go in this way in one direction, in the opposite direction in another way. So that's a bit more difficult to envision. But the idea should be quite clear. That's a negatively curved space, two-dimensional space.
Just at this point.
What?
In this point.
No, it's every point. It's hyperbolic.
The surface here, no surface with constant negative curvature, which is also closed.
So close. I
Not
didn't say it's close.
Not closed.
The
It's the boundary.
space doesn't have to be close.
The boundary inside.
The boundary is just for me to
No,
to
אם
picture.
אתה קוטע אותו, אז צריך להוסיף את
There's
המהירות על
a
השפה.
hypersphere, I think it's called.
It's fine. We'll talk about that.
אבל בוא שים
It's not going to be closed. That's okay.
It's not. I think it's not smooth.
So what?
I think it's not smooth. It's boundary inside.
No boundaries. We don't. You'll see that. We'll talk about the universe as a universe. You'll see that. Okay, that's just to give you the idea and to show you that you can actually do these calculations. It's not that terrible.
Is it possible to embed something like this in 3D Euclidean space?
What?
Is it possible to embed something that like this that's negatively curved in 3D Euclidean space? Like a sphere you can. This.
It's not a closed space. This is a closed space. But in principle, you can envision that. But why? I mean, you know, I draw it on a line, right? On a Euclidean board, right? A flat board. You can, but you know, the whole idea of what we're doing here, right, is that we can learn about the curvature of the spaces without looking at the outside, without looking at higher dimensional space, without assuming it's embedded in anything else. Just by sticking to the space we have, you can understand the properties of the space. Again, always think of it in terms of ants. We are ants, we have no way of looking outside. we've got no way of looking outside of our universe, saying whether this universe is embedded in somewhat higher dimensional universes. Maybe it is, I don't know. I don't know. I don't have any way of telling, and I will not have any way of telling before I die. So I just have to assume it's irrelevant for anything I do. Okay. The ideas is good ideas. You get more problems today to solve. So, any questions about that? You okay? I'm not doing too fast. You guys are. Again, I don't want to discover that I'm going too fast in the exam. That would be too late. Now is the time to make sure that things are clear in your mind, and I know they're not, because they're not supposed to be clear in your mind after first hearing that. They're supposed to be clear in your mind after you do your homework and after you read the textbook again in books, in my lecture notes, in everywhere you prefer to use your resources. Okay, now there is another small part which I'm going to skip because this is a short semester. I just mentioned it to you, and if we make another tutorial, I'm saying if because I'm not sure when we can have it, but then I will try to show it to you. It's mainly mathematical, and it's called the geodesic deviation. So I'm just mentioning it to you. It's in my lecture notes. I'll put it. You can read it there. You know everything you need to know to find it right now. Remember, when we were young, at the beginning of the semester, we discussed this elevator experiment, right? This we have an elevator, and there are two scientists inside, and the elevator cable is broken, and then they freely fall. And the question was whether they can measure gravity, right? And the answer was no, to zeroth order. But we said there is a first order effect, which is what? Second order. Second order effect, which is what?
They are following one time.
So, yes, exactly. So both are attracted towards the center of the Earth, right? So their vectors are not exactly parallel to each other, but they are slightly, there's small deviation, which means that if they wait long enough and they have an accurate enough measuring facilities, they could tell that they are by seeing that they will get closer to each other, right? Have a small component that takes them closer to each other, right? So this small component is what's called the geodesic deviation. The idea is that I have a particle somewhere here, and I have another particle nearby that particle at some location at delta x for me. And then I can calculate what will be the change of delta x. Okay, so it's a technical calculation. It's not too long, but I don't want to spend time on that right now. And the answer is that d squared delta x mu over d tau squared, just giving you the answer, is r mu rho sigma alpha dx rho over d tau dx sigma over d tau delta x alpha. That is essentially the equation that tells you if you're taking two particles which are within a gravitational field or within any space which is not flat but has some curvature, this geodesic deviation tells you how the deviation between them changes along the trajectory.
Why is the D?
What?
Why is the D capital?
Just the way of doesn't really have to be capital.
Because
That's a good question.
we use D.
Maybe this is my. Why did I use that? it's of course it's a covariant derivative, right? So the d represents a covariant derivative. All right. So I'll ask Akshay to prove you this equation. So you know that it exists. So basically now you have all the tools that you need to know how to make measurements in any curve perspectives. All right. Just told you that I did not prove it. You know it's there. And the reason why I didn't do it is because this semester is a bit shorter than usual. And although we're doing fine right now, I don't want to spend too much time. I want to go straight to the next subject. So let's do it now.
Will the form of this equation
What?
come up later?
Sorry?
Will the form of this equation come up later in this course?
I don't think so. Otherwise, I would spend time. Maybe you can come in next. All right. Einstein's field equation. So finally, we have everything we need to derive Einstein's equation. Again, this is the heart of general relativity. I mentioned it to you. I spent half semester deriving Einstein's equation and the second half solving Einstein's equation. That's basically what this course is all about. The basic idea, this is the ingenuity of Einstein. Existence of mass or energy, E is equal to mc squared, curves space-time. Space-time is not flat, it's curved, and the thing that curves it is mass. Energy, mass, energy, curves, space-time. Now, of course, there is more than one way of deriving Einstein's equation. Today, there are several. In textbooks, you can find at least 2 or 3 ways. I'm going to use a way which is slightly hand-waving, not really, and it's quite close to the way Einstein himself derived it back in 1950. You can find it, if you go to textbooks, there are several ways of deriving it. So, in classical mechanics, right? What is the equation that we want to replace in classical mechanics?
G and 1, G and 2.
Cannot hear you.
G, the classical force of G and 1 and 2.
Yeah, we grew up from that, right? What will be the generalization of that? Poisson equation. Right? I have a Poisson equation. Classical mechanics.
So the equation relates potential to source. Does it give us any?
W squared phi is equal to 4 pi g rho. Right. Why do I write phi? Normally you write this minus gm over r, right? I don't write it. Why I don't write it like that?
It's only true for a point.
Because it's what?
Only true for a point.
Exactly. This is true only for a point particle. And rho, what is the rho?
Mass
Distribution of particles.
So
Right?
this isn't any dynamical equation.
No, it's okay.
Static equation.
Yeah, it's okay.
Poisson equation.
No, it's fine. Rho, mass density. So we want an equation that's going to replace this equation, and of course, in the relevant limit, which is what? The weak field limit, right? Which we already discussed. In the weak field limit, we have to get back this equation, otherwise we're doing something wrong. Right? What is phi?
Gravitational.
Potential, right? So phi, gravitational potential. So what do we want? We want an equation. What do we know about this equation that we want? What do we know about it already? Sorry?
It's going to be a tensorial equation.
Yeah, so it has to be a tensorial equation, that's correct. So we look for, we want tensorial equation, retrieve back Poisson equation, in the weak field limit. What do we really have here? What is here? The second derivative of the potential. What will replace the second derivative of the potential? Exactly, curvature. Right. What do we have here? Distribution of masses. What will replace that? Stress energy tensor. Right? So this would go into a team union. That's quite obvious. I didn't waste time introducing you the stress energy tensor from the thing.
How is this energy tensor defined with masses? Defined for a perfect fluid. How is it defined for anything else?
We define it for dust.
Right.
We define it also for dust, which is a perfect fluid, right?
Yes, but dust is a perfect fluid.
Exactly.
We did define it for the general distribution of masses within the general fluid.
We did.
No.
The thing that we did not add to that were things such as viscosity and
We defined it from the perfect fluid.
it was defined, yes.
everything.
That's fine. I said to zeroth order, even to first order, everything we deal with is perfect fluid. Star is made of perfect fluids. Distribution of stars in the galaxies are perfect fluid. Galaxies in the universe act like perfect fluids. Everything is a perfect fluid. Huh? Don't worry about that. It will be much worse things, worse approximations. That's actually quite a good approximation. If you want, you can add viscosity. That's fine. I said you can stress energy tensor. The place where you're supposed to see that in is classical fields, electromagnetic fields. You can see it here. Now we didn't, but it appears in various branches of physics. Right? If you do fluid dynamics, okay, not basic fluid dynamics, maybe advanced fluid dynamics, it will also appear. And you can simply add viscosity. It's fine. Here we're doing relativity, so let's stick with that.
If we have a collection of point masses.
Yeah. What's that? That's a dust.
Collection of point masses.
Is a dust. Collection of point masses is a dust. Actually,
No.
it's a fluid because that depends on the, they can be at rest relative to each other, right? And so these are stars. But now I'm an astronaut. I'm traveling in my spaceship, so relative to me, I see all of them moving, right? I'm in a boat sailing the ocean. Relative to me, everything is moving. It may not be moving relative to each other, but it is moving relative to me. Huh?
But if we don't have enough point masses to treat it as a continuum.
Okay. We do for the purpose of this course.
If we don't.
Then we worry about that in the next course. What did we say replaces the gravitational potential? What? The metric tensor, right? So this will be the metric tensor. Now remember, in the weak field limit, we had, what did we have? we had G00 was minus 1 plus 2 phi, and T00 rho. And I wrote G mu nu as eta mu nu plus h mu nu. Right? So if I have it here, then I can write down from here to have nabla squared h00 is minus 8 pi g t00. Or h00 is just a 2 phi we have. Well, that's not the tensorial equation. Why it's not? That's not the tensorial. That's not the tensorial. Right? So how can we generalize this with a tensorial? Make it tensorial. Laplacian. Yeah, I can try. So it will be replaced by what? Minkowskian, right? The D'Alembertian, sorry, right? So this will be a, sorry, this is going to be a D'Alembertian, right? Cheers. Nabla mu, nabla mu. No, I can't do that. I mean, I can, but it's not going to get me too far. Why? Why not? What's the problem? You said it to me. What's the problem?
Oh, it's zeroed out.
Zero, right? Because nabla mu of g, right? Nabla mu g mu nu is always zero. Symmetric compatibility. So that's not a good idea. So what do we put on the left hand side?
Something instead of g.
Something instead of nabla squared D'Alembertian of g, right? What would you guess if we should put here?
R.
R, right? That's a good idea. If I try to put the Riemann, is it going to work? Why shouldn't I put the Riemann tensor here?
No, because it also zero.
Why not? It's not zero. Riemann I can do, but I cannot put it here. Why cannot I put the Riemann tensor here? What's the problem?
Too much indices.
Too many indexes, right? I don't have the same number of indexes. So I can put the Ricci or the Einstein. Let's start with the Ricci, because Einstein first thought of the Ricci. Right? So if I try to put the Ricci, what will happen? So
Which is scalar or which is tensor?
which one? Answer that.
We need the same number of indices.
It needs to be a tensorial equation, right? So we have only one option.
The scalar.
No. What do I have here on the right hand side? Right hand side I have T mu nu. I have two indices. So what do I have to put in the left hand side?
Two indices.
Two indices.
Two indices from g.
We said if I try to put G and I do the D'Alembertian, I get a zero. So I need another tensor.
We need another tensor other than g. Okay.
Yes. Now the Riemann tensor, the Ricci tensor is actually quite good, because how did we get the Ricci tensor?
Second derivative.
From the Riemann. And how did we get the Riemann?
Second derivative.
The second derivative of the metric. So in terms of derivatives, we're okay. So what happens if we try R mu nu equal kappa T mu as an equation? Right? And kappa is some constant. So it's going to work.
No, because this is
Supposed to be
conserved and R would not
physically. What am I missing here? Conserved, yes. What is conserved? What quantity is conserved?
the stress energy.
Energy. Very good. Very good. What is conservation of energy? Remember that? Right. Conservation of energy. conservation of energy. Exactly. Nabla mu T mu nu is equal to 0. Right? Which means that we should get nabla mu R mu nu equal to 0. But that's not always true. Right? Exactly. It's not true because of Yankee identity. Right? We just showed that. We just solved it. Right? But Bianchi identity and that nabla mu R mu nu is 1/2 nabla nu R. So if we put it here, we put R here, so we're making a construction. And R is equal to kappa G mu nu T mu nu, or kappa T, which means that nabla mu T would be equal to 0. Which means that T should be always constant. T is not constant always, because, right? In vacuum, what is T? 0. And inside a star, what is T? Something which is not 0. So that cannot be. So we already said it, right? So instead of R, we should put a G. But if we write G mu nu, it's R mu nu minus 1/2 R G mu nu. What is nabla mu G mu nu?
0.
By what? This is what? This is the Bianchi identity. But this also means what? It's in here. What is written? What? Conservation of energy. Ah. So Bianchi identity is not just a mathematical identity. It's also conservation of energy. Okay? It's not just the math. We did a lot of maths, but now we're putting the physics in it. Okay, so we're gonna try now the equation of the form G mu nu is equal to kappa T mu nu. Again, kappa is some constant. So this has all the requirements that we want. Right? The tensorial equation, same number of indices, energy is conserved, right? The question is this the correct equation? So for that, you have to do contraction and do the weak field. So let's see what we get. So let's do the contraction. So contract G mu nu G mu nu G mu nu of R mu nu minus 1/2 R G mu nu. What is G mu nu R mu nu? R minus 1/2 R G mu nu G mu nu is equal to kappa T. What is G mu nu G mu nu? How much?
Minus 2. Delta. Wait. Okay. So,
What is G mu nu G mu nu?
4.
4. Thank you. Yeah. So if we plug that in here, right, and this is the definition of G mu nu, or is minus KT, then we have that R mu nu is kappa T mu nu minus 1/2 T G mu nu. Okay, so it's the same equation, just written slightly differently. Now we want to see if we get back the Newtonian limit. So, Newtonian limit, Newtonian weak field limit. What is rho? Mass density. What is rho?
T00.
T00, right? Rho is T00. Again, Newtonian means everything moves. That for me, that simply says, right, the kinetic energy is much more than the rest mass. mc squared is much greater than gamma minus 1 m. Okay, that's what it really means for me, right? Or kinetic energy can be neglected relative to the rest mass. Now, since the 0,0 term is going to be much greater, then I can throw away all the other terms because they're too small. So just look at the mu. Look at mu equal to 0. And we had G mu nu is eta mu nu plus h mu nu with h much more than 1. So we have G 00 is a minus 1 plus H 00, and G inverse is a minus 1 minus H 00. And the trace of the energy momentum tensor, T. What? So T is a G00 T00, right? Which is just a minus T00. I can throw away all the smaller order terms. And then I'm going to plug this in the proposed field equation. So an R00. I can use a 0, 0 here.
Why are the other terms in T are negligible?
What?
למה שאר האיברים ב-T? למה אתה יכול לקחת רק את 0,0 ולא גם
כי כל השאר כוללים את התנה. Everything else is, this is the rest mass. I mean, remember, right? Weak field means that all the kinetic energy, all the momentum are much, much smaller than the rest mass.
Much bigger than F.
What?
So T00 is much bigger than F.
Yes, because it contains the rest mass. It's the only term that contains the rest mass energy. You see that? You have to look at to play a little bit with that in your head at least, right? The stress energy, so it tells how much momentum you have, what is the flux of momentum, which is the flux of energy. But the main flux of energy is always because of the, in the weak field, that means that it's a rest mass dominates. So R00, if we plug it in, this is a minus, right? So we have the minus here, that's fine. So we have, that's going to be 1/2 kappa T00. Okay, that's from here. There's a minus, G is a minus, we have here a plus, half, that's fine. Now we actually need to derive that. So, now R00 is an R lambda 0 lambda 0, but all the 0, 0 terms, what are they? 0. So we just need to evaluate r I0, I0. Remember, I Latin indices just goes from 1 to 3. We have r I0, J0 is dj gamma I00 minus d0 gamma I J0 plus gamma I J lambda gamma lambda 00 minus gamma I 0 lambda gamma lambda J0. J0. What is that? What is that? What is that? Zero, right? It's a time derivative, right? It's a time derivative, and we said the weak field limit, things are not changing this time. Right, so this is 0. These two terms, I argued they are small because gamma is going to be small anyway. So I can neglect these as well, arguing that they are small. So what we really care about is that part here, and so we have r I0 is di gamma I00, which is di 1/2 gi lambda d0 g lambda 0 plus d0 g 0 lambda minus d lambda g00. Again, the time derivatives of the metric, I don't care about them. So we have a minus 1/2. Again, to zeroth order, g is just eta. So we have an eta I j di dj h00, which is simply minus 1/2 lambda squared h00. Which means that in the Newtonian limit, so in the Newtonian limit we got that nabla squared h00 is minus kappa t00. Right, this is equal to that, right? Just plug it in here. Plug it in here, I got h00. Right? Nabla h00, nabla squared h00. Right? Nabla squared h00 is minus kappa t00. This derivation was done in the Newtonian limit. What did we get from Poisson equation? Right? So that h00 is 2 phi. And we got 2 phi was 8 pi g. So what does it mean? I can write down kappa as if I identify kappa to be, so for kappa equal 8 pi g, we retrieve back the Newtonian limit. I already erased that, but so now I can finally write down Einstein's equation. Which is what? G mu nu, I'll just write it down explicitly. R mu nu minus 1/2 R G mu nu is equal to 8 pi G T mu nu. That's Einstein's equation. So minus here. Right. One step at a time. No point in jumping, we'll get to everything. What do we have here? Just look, that's a tensorial equation. Now I'm talking about physics. Right? We're done with the maths for the time being. We will have more maths, don't worry. But for the time being, we're done with the maths. Now we're talking about physics. The right-hand side is what?
The matter.
It's a matter. It tells us what is the matter content of the universe. The left-hand side
Or geometry.
is geometry. Einstein managed to connect two things which seems to be completely disconnected. One is the geometry of space-time, and one is the mass content of the universe. Not necessarily of the universe, right? So this essentially tells us, expresses how the presence of energy acts to curve space-time. Acts curve space-time. As I promised you, what we're going to do from here on, the next there was left from the semester, just one half, is to look for solutions to this equation. In fact, in this course, we look for two solutions. I'll mention it one. One is a solution in vacuum. What do we mean by vacuum? No matter.
Zero.
Right, zero matter. So what does it mean, no value? So that means that everything here is, the right-hand side is zero. So one solution you already know. What? Minkowski. Right, Minkowski, so now the solution, 0 equal to 0 basically. Apparently there is another solution. There are more than one. Another solution which we'll discuss is called the Schwarzian metric. Right? It's also a solution for T mu equal to 0. Now there is another solution, which is, we're going to use some simplified assumptions, which is there is a matter, but it's evenly distributed. That goes back to your question. Assuming that the matter is evenly distributed in the universe, we'll get to another solution. That's called the Robertson-Walker metric, Friedman-Robertson-Walker metric, and that's a metric that describes the universe as a whole. That's cosmology. That's the basics of cosmology. That's where cosmology starts. Cosmology is a description of the universe, not of a single object, but the global structure of the universe we live in. We will not have time to discuss gravitational waves, and it doesn't really matter that much because gravitational waves is really a perturbation. It's a perturbative solution of Einstein's equation. So if you get the ideas to get the perturbative, it's just reading a chapter in a book and you see it's not that conceptually more difficult than anything else we're going to do. Just one thing. How did we get to this equation? How do you get this R? We started from the metric. We calculated the affine connection. We calculated the derivative of the affine connection to get so the first derivative of the metric is the affine connection, then the second derivative of the metric to get the curvature, and then the contraction. It's damn hard. It's damn hard. It's not linear. What does it mean that it's not linear?
When you add the matter, it's not.
It means that if you happen to know two solutions of Einstein's equation, a linear combination of this solution is not going to be a solution by itself. That's what it means, it's not linear. So we don't know all the solutions of Einstein's equation. There are known solutions. There are a few known solutions, but there is no way for us to know that we found all the solutions. In fact, there are people who devoted their careers today to try and find solutions to Einstein's equation. Yeah.
Is it chaotic?
In what sense, chaotic? I don't understand what you mean by chaotic.
Changing T mu a bit is.
I don't know. I don't know the solutions right now. I'm not an expert in finding various solutions to Einstein's equation. There are numerical ways. It's not chaotic in the sense that there are perturbative ways of finding solutions. For example, gravitational wave is a perturbative way of finding solutions when you have two stars that evolve, right? And then the metric evolves in time, but in a certain way that you know how it evolves. Right? Yeah.
You said that for t mu nu equals 0, we have 3 solutions.
T mu nu equal, no, we said that, I said for t mu nu equal to 0, we'll discuss one solution. I mean, one solution,
We
okay.
can't know if we find all this. Can we?
Do we know that we find all the solutions? No, we don't.
Even for t equals 0,
What?
Even for t equals 0, there might be more solutions.
Possibly, yes. I have to be a bit careful here because there are several solutions known. The solutions will lead to black holes, and there is a no-her theorem of black holes, meaning black holes themselves can be described only in certain finite number of free parameters. But there could be other solutions for that as well, also. I cannot go much further because I'm no expert in additional solutions. So the solution that we're going to discuss is a Schwarzschild solution. That's the first solution that was found. There are other solutions. One is called the Nordstrom, I don't remember the other name, which is charged black hole. And there is a solution, the Kerr solution, which is a rotating black hole. We will not have time to discuss the solutions of this solution.
Neutron or charge?
What?
Neutron spinning black hole?
Yeah. In nature, there are no charge black holes. So if black holes can be formed charge, but then they will just discharge very rapidly. In nature, we do find Kerr black holes. We know that. Okay, we won't discuss rotating black holes here. We don't have time. We will discuss black holes. We're going to save that out. Essentially, it's a solution, and of course, there is a Minkowski solution. No, it is not contradicting because the theorem states that you have an asymptotic. The Schwarzschild solution will be correct in the asymptotic limit of flat space. If the asymptote is not a flat, you can think of partial solutions. Okay. One more thing about that. How many equations are here?
16, but not
There are 16, yeah, but they're not all independent. Right? In fact, there are six independent solutions, 6 independent equations here. So it's already quite cumbersome because you have the 10 solutions. You have the Bianchi identity, which add up 4 constraints, which essentially is conservation of energy. 10 equations you can see right away, right? Because it's symmetric in mu and nu. Everything here is symmetric. So out of 16 you get a 10. But then you have the Bianchi identity, which will give you 4 constraints. Right? Nabla mu of g mu is equal to 0. That's another 4 constraints. So you have 6.
Isn't the Bianchi identity doesn't reduce the number of dependent components in
No, it doesn't. It just adds up. And I have to be careful that I'm not lying to you now. I think it does not, because it's treated as a conservation of energy. Okay, I think that's a good place to stop.
Question.
Yeah.
How does this equation change if you go from 4 dimensions to 3 and 2 dimensions?
I need to think of an answer because I never thought of that in 2 or 3 dimensions. So I don't know what it really means. I mean, all the metric that we derived, in principle, you can derive the mathematics will be the same, right? What we derived for a metric, for the curvature, for the Ricci, will be the same. I honestly, I don't know. I'll try to check out what does it mean if you do it in 2 or 3 dimensions. I just never thought of that. All right. Okay, we'll get the next problem set.
You introduced another way to draw ice conditions, like the least action.
Yes, there are. You can do it using least action. You can do it in more than one way. Right, the Hilbert action. You can do many things. I'm not going to do it because of lack of time. You can find it in textbooks. Basically, every reasonable textbook, the textbook of Carroll, I know for sure have another derivative, and several other textbooks as well. So it's not difficult to find other derivatives of the function equation. All right. Okay, have a good weekend. Now we're going on the weekend, actually, right? That was not the weekend. Now we're going on the weekend, so I'll see you all on Sunday, but please try to be on time. You know the traffic for Sundays, so try to plan accordingly. Yeah.
כאילו, יש לנו רק ב-R ורק ב-RE ורק בריצ'יטן, כאילו, אנחנו עושים, מחלישים מאוד את כל הכמויות של המרחב.
ממש לא מחלישים שום דבר.
כאילו, אבל צמצמנו
אין פה שום החלשה. אין פה שום החלשה. יש פה ההפך, אם כבר זה לתמצת את הפנימיות לתוך ה... כי הערכים שאתה מקבל הם... השאלה איך אתה מתאר הפנימיות. זאת אומרת, יש פה... אני יודע שלא...
כאילו יש לי טנזור עצום, 20 ערכים.
נכון, אבל גם ל-R new יהיו לך